Today we are going to learn about optimizing GPU memory usage for machine learning. In this video, we'll explore how to efficiently manage GPU memory, ensuring maximum performance and cost-effectiveness in your machine learning applications.
Welcome to our video on optimizing GPU memory usage for machine learning. With the exponential growth of machine learning models, efficient GPU memory management has become a critical aspect of performance and cost management. In today's session, we'll cover the essentials of GPU memory architecture, techniques for memory allocation, strategies for memory pooling, and more. By the end of this video, you'll have a solid understanding of how to maximize your GPU's resource utilization, ensuring that your machine learning tasks run smoothly and efficiently.
Let's start by understanding the architecture of GPU memory. Unlike CPU memory, GPU memory is designed to handle parallel processing efficiently, which is crucial for tasks like machine learning. The core component of a GPU's memory is VRAM or Video Random Access Memory. VRAM is responsible for storing image data that the GPU can access quickly. This is vital for rendering graphics, but it's also crucial for processing large datasets in machine learning. Another key aspect is memory bandwidth, which determines how quickly data can move in and out of the GPU. High memory bandwidth allows for faster data processing and is essential for optimizing performance. Understanding this architecture helps in making informed decisions about memory allocation and usage. Effective memory allocation techniques are crucial for optimizing GPU memory usage. There are two main types of memory allocation: dynamic and static. Dynamic memory allocation allows programs to request memory as needed, which can lead to efficient usage but requires careful management to avoid leaks. Static memory allocation, on the other hand, reserves a fixed amount of memory, which can be wasteful if not fully used. Best practices for memory allocation include profiling your application's memory usage and adjusting allocations based on the model's needs. Tools like CUDA's memory allocation functions can help in managing memory effectively. Avoiding memory leaks is essential, as they can lead to wasted resources and degraded performance over time. Memory pooling is a technique used to optimize memory usage by reusing blocks of memory for different tasks. This can significantly reduce fragmentation and improve the efficiency of memory usage. By implementing a memory pool, you can allocate a large block of memory upfront and then subdivide it as needed for different operations. This reduces the overhead of frequent allocation and deallocation, which can be costly in terms of performance. Benefits of memory pooling include reduced memory fragmentation, improved performance, and more predictable memory usage. Implementing memory pooling involves creating a pool manager that handles the allocation and deallocation of memory blocks, ensuring that memory is used efficiently and effectively. In environments where multiple GPUs are used, balancing the memory load across different units is essential for optimal performance. Load balancing ensures that no single GPU is overwhelmed with data, which can lead to bottlenecks and reduced performance. Techniques for distributing memory load include data parallelism, where data is split across GPUs, and model parallelism, where different parts of a model are processed on different GPUs. The benefits of a balanced memory load include improved performance, reduced processing time, and increased efficiency. Tools like NVIDIA's NVLink and CUDA-aware MPI can assist in managing load balancing across GPUs. However, challenges such as data synchronization and communication overhead need to be addressed to ensure smooth operation.
Memory profilers are powerful tools for identifying memory usage patterns and potential bottlenecks in your applications. They provide insights into how memory is allocated and used, which is crucial for debugging and optimizing performance. Popular memory profilers include NVIDIA's Insight Systems and CUDA-MemCheck, which offer detailed reports on memory usage. Interpreting profiler data requires an understanding of memory allocation patterns and the ability to identify memory leaks or inefficiencies. By using memory profilers, you can make informed decisions about memory allocation, identify areas for improvement, and ultimately enhance the performance of your machine learning models. Best practices for profiling include regular monitoring of memory usage, setting appropriate thresholds for memory alerts, and continuously refining memory allocation strategies based on profiler feedback. Memory fragmentation occurs when free memory is broken into small, non-contiguous blocks, which can lead to inefficient memory usage and degraded performance. It is often caused by frequent allocation and deallocation of memory, leading to gaps that cannot be easily reused. The impact of memory fragmentation on performance can be significant, as it reduces the available memory for large allocations and can increase access times. Techniques to minimize memory fragmentation include using memory pools, careful management of memory allocation patterns, and defragmentation strategies. Benefits of reducing fragmentation include improved memory utilization, increased performance, and smoother operation of machine learning applications. Case studies have shown that addressing memory fragmentation can lead to significant improvements in performance and resource utilization.
Data transfer between the CPU and GPU is a critical aspect of GPU memory optimization. Inefficient data transfer can lead to bottlenecks and reduced performance. Techniques for efficient data transfer include using asynchronous data transfers, minimizing data transfer size, and optimizing data transfer patterns. Asynchronous data transfers allow data to be transferred while other operations are being performed, reducing idle time and increasing throughput. Reducing data transfer overhead involves minimizing the amount of data transferred and maximizing the use of available bandwidth. Tools like NVIDIA's Kublas and Qt can assist in optimizing data transfer. Case studies have demonstrated that efficient data transfer methods can lead to significant improvements in performance and resource utilization. Tensor operations are at the heart of many machine learning applications, and optimizing these operations is crucial for efficient GPU memory usage. The importance of tensor operations in machine learning cannot be overstated, as they are involved in every aspect of model training and inference. Optimizing tensor operations involves techniques such as using efficient libraries like TensorFlow and PyTorch, optimizing memory access patterns, and utilizing hardware acceleration features. The impact of optimized tensor operations on memory usage can be significant, leading to reduced memory requirements and improved performance. Tools for tensor optimization include NVIDIA's Kublas and Qt, which provide optimized routines for common tensor operations. Real-world examples have shown that optimizing tensor operations can lead to substantial improvements in performance and resource utilization.
In conclusion, optimizing GPU memory usage is a critical component of effective machine learning applications. We've covered a range of topics, from understanding GPU memory architecture to implementing memory pooling strategies, balancing memory load across GPUs, and avoiding memory fragmentation. By applying these techniques, you can achieve significant improvements in performance and cost-effectiveness. Remember, efficient memory management not only enhances performance but also allows for the development of more complex and powerful models. We encourage you to apply the knowledge and skills learned in this video to your own projects, ensuring that you make the most of your GPU resources.